Hello! Yes, and welcome to our Objective 5.5 notes. Objective 5.5 says, I can write a polynomial in factored form given the real or complex zeros, and that, my friends, is going to be what we do today. So we're using this word zeros. What are zeros? Zeros are represented as the x-intercepts on the graph. All right. So think about when we have a polynomial, when we would solve for a polynomial, we are finding the x-intercepts. We're finding the zeros. Now, one thing that can occur with polynomials is this thing called multiplicity. Multiplicity is multiple zeros at the same value. Now, one of the easiest ways to identify the zeros of a polynomial function is to look at it in factored form. So that's going to be how we focus on this idea today. So let's look at these three functions here, all polynomial functions. So remember, if something is in factored form, to find the zero, all we need to do is set it equal to 0. So this is just like when we were solving quadratics by factoring. If we have a factor that's x, we would set it equal to 0. So x equals 0. X minus 2. Set equal to 0, that means x equals 2. X plus 4 set equal to 0, that means x equals negative 4. Now, one of the unique things about multiplicity is how it is identified, and it's identified by the exponent, because what this exponent says is that we have two factors of x minus 2, which means we have two zeros at 2. So if we were to state the zeros and identify any multiplicity, we'd say x equals 0, x equals 2 with a multiplicity of 2, and x equals negative 4. So those would be our zeros for this first one. So let's look at B here. So x minus 3 would give us the factor of x equals 3, and notice we have a cube, so that means it's being 3 factors in our polynomial, so it would have a multiplicity of 3. 5x plus 1. So if I set 5x plus 1 equal to 0, I'd subtract 1. So I'd 5x equals negative 1, so x equals negative 1/5. All right, so that would be another 0. X equals negative 1/5. And then my final 3x minus 2 is a factor. That would mean x equals 2/3. So there would be my zeros for this one. Now, looking at C, 3x plus 5, 2x minus 7 to the 12th. Wow. So x equals negative 5/3 for my first factor. And then x would equal 7/2 with a multiplicity of 12. So we would have 12 zeros at that multiplicity. Now, zeros in multiplicity impact the graph. All right. So if a zero has an odd multiplicity, that is to say it occurs 3 times, 5 times, 7 times, an odd number, then the graph goes through the x-intercept. However, if a zero has an even multiplicity, it occurs 2 times, 4 times, 6 times, 8 times, the graph bounces is the verb I use. The graph bounces off of the x-intercept. So, quick sketch, going through would look like this, and then like that, and then something bouncing would look like that. Right? So this would only look like we have 3 zeros, right? We have 3 x-intercepts. But this one would be an even multiplicity. And these two would be odd multiplicities. If it goes through, it's odd. If it bounces, it's even. All right, so what we're going to do now is we're going to kind of switch the process. We're going to flip it. Instead of identifying the zeros, we're going to write the polynomial in factored form. Now, one of the things here is integer coefficients. All right, integer, remember, think is a positive or negative whole number. So no fractions in our zeros. So let's look at letter A here. If x equals 2, what factor would give me an x equal 2? Well, that would be x minus 2. If x equals negative 1, what factor would give me negative 1? X plus 1. If x equals 3, what factor would give me 3? X minus 3. Now, notice that's multiplicity 2, so we show that with our exponent. So this would be the equation for these zeros. Let's look at letter B here. X equals 2 thirds. So think about this. How would I get 2/3 without fractions, right? I need to create a factor. Well, let's look up above here, right? X equals 2/3 was in letter B. That was from the factor 3x minus 2. Oh, okay. So this number, the last number, the constant here, would be our numerator, and the coefficient is our denominator. So if x equals 2/3, well, we just looked at that one. That would be 3x minus 2. Negative 1/2 would be 2x plus 1. We have x equals to 0, so that's just x. Now it has a multiplicity of 2, so x squared. And then x equals 1x minus 1. So that would be our function with the stated zeros. Let's look at C here. X equals 1/2, 3 multiplicity of 3, and a negative 5 multiplicity of 2. So our function, f of x, would equal, to get the factor, or to get the 0 1/2, we would use the factor 2x minus 1. For 3, we'd say x minus 3, multiplicity of 3, so show that in the exponent. Negative 5 would say x plus 5, multiplicity of 2, show that in our exponent. And our last one here, look at all these multiplicities. We got some fractions. This is a good one. So we'd say f of x equals x for the 0, 1/5 with a multiplicity of 4. So that would be 5x minus 1, and then our exponent. 2 with a multiplicity of 2, x minus 2, and then our exponent. Negative 3, x plus 3, our exponent for its multiplicity. And there we go. So hopefully we're feeling pretty confident with these. I'm going to add another twist here. So we've been working, or in the past we worked with imaginary numbers. So it's possible to have what's called an imaginary zero, or a complex zero. And this is all centered in the fundamental theorem of algebra. A polynomial of degree n has n zeros in the complex number system. That's to say, if the polynomial is x to the 4th, as its highest degree, it has 4 zeros. If it's x to the 7th, there are 7 zeros. Now, by knowing how many zeros a polynomial has, we know how many factors we're going to need, right? So irrational and imaginary zeros are zeros that are not x-intercepts. They are not real zero. Well, they are not rational zeros. The irrational one are still real. The imaginary are obviously not real. They're imaginary. So the irrational will still be x-intercepts. The imaginary will not be x-intercepts. And one of the great things about these is they occur in conjugate pairs. Now, this may be our first exposure to conjugate pairs. So conjugate pairs is a very straightforward idea. All we need to do is switch the sign before the radical, or switch the sign before the imaginary. So if negative 13 is a 0, positive square root of 13 is a 0. All right? The linear factors would be x plus root 13. That's what this one would become. And x minus root 13. That's what this one would become. If 2 plus the square root of 3 is a 0, well then 2 minus the square root of 3 is a 0. Now these zeros, we'd have x and then just switch our sign, so minus 2 minus root 3. That'd be this factor, x minus 2 plus root 3. So notice the sign in front of the radical changes. Now what if it's an imaginary number? Well, the complex conjugate of an imaginary, the sign changes before it. So if it's negative 4 plus 7i, it's now negative 4, or the pair, the conjugate pair would be negative 4 minus 7i. So our factors here would be x plus 4 minus 7i, right? We switch all the signs. That'd be this one. And x plus 4 plus 7i. That'd be this one. So if negative I root 37 is a factor, then positive I root 37 is also a factor. So if we have our factors would be x plus I root 37 and x minus I root 37. So what we're going to do now is we're going to build on what we just did, only this time now we're also going to include complex and imaginary zeros. So let's walk through. Let's look at this first example here. X equals 3 and 2 plus I. Well, remember, imaginary zeros occur in conjugate pairs. So if 2 plus I is a 0, we also know that 2 minus I must be a 0. It's impossible to get a complex or imaginary 0 without its pair. They will always occur in pairs. So the factors for this one would be f of x equals x minus 3, x minus 2 minus I, and x minus 2 plus I. All right, let's look at letter B here. So f of x, a 0 of negative 1, so that's x plus 1 as a factor. A 0 of 4, so that'd be x minus 4. Now multiplicity 2, so that tells me it's squared. And then we have 3 minus root 5, so that's a complex. Or sorry, that's an irrational. So if 3 minus the square root of 5 is a 0, 3 plus the square root of 5 is also a 0. So that means we would have x minus 3 plus root 5 and x minus 3 minus root 5. And that would be our factored form. All right, look here. So x equals 1 minus 4i. Well, if it's 1 minus 4i, a 0 must also be 1 plus 4i. And then our other one is 4 plus the square root of 2, so its conjugate pair, 4 minus the square root of 2, must also be a 0. So this one has 4 factors, right? So let's create what those factors are. So we'd say f of x equals x minus 1 plus 4i. That'd be this one here. X minus 1 minus 4i. That'd be this one. X minus 4 minus root 2. That'd be that first one. And then our conjugate pair, x minus 4 plus root 2. Those would be the factors for the polynomial with these zeros. Now for this last one, let's see here. We have f of x equals a 0, so that's just x. Negative 7 is a 0, so that'd be x plus 7. 2 is a 0, so that'd be x minus 2, and it has a multiplicity of 3. So 3 would go there. Now 3 minus 7i is a 0, so its complex conjugate 3 plus 7i must also be a 0. So I'd have x minus 3 plus 7i and x minus 3 minus 7i. Hopefully that makes sense. If you have questions, definitely reach out. If you're feeling really confident, feel free to look at those practice problems. Otherwise, check out those sample problems and watch that video where we do a few more.